Okay, welcome back. Today, we're going to be talking through Chapter 6, which is about normal distributions and z-scores. Now, we've been talking a good bit about measures of center and spread. We talked about all these different types of ways to measure the center, the mean, the median, the mode, all these different ways to measure where the data is centered. And then we talked about spread. We used IQR a lot, but we didn't talk very much about what standard deviation really means. We mentioned that it is a measure of how spread out the data is, but we didn't give a good example of how you can interpret that number. Because the standard deviation works differently depending on the shape of the data. But for data shaped in a very specific way, the standard deviation is very easy to interpret. That specific shape is called the normal distribution, and it's what we are going to look at today. The normal distribution, which you might have heard of as the bell curve, is a model that we can use to describe a parameter that varies about a central value. Not everything is normally distributed, but many things are. And the shape of the bell curve would look much like this. We've got a mean, which is where the data is centered, marked with a Greek letter mu, which looks like a fancy U, or if it was just a sample instead of the whole population, an X with a bar over it. We know how mean works. We know how to calculate the mean of a set of data, so we won't talk more about that. The standard deviation, which is this Greek letter sigma for the population, or simply S, if we're working with a sample, is a measure of how spread out the data is. A standard deviation you can think of as an amount away from the center that you can be. So you might be 3 standard deviations above the mean, or 2 standard deviations below the mean. If the standard deviation is very large, then it is normal for data to be very far away from the center. Whereas if the standard deviation is very small, then we would expect our data to be more clumped together, and data very far from the center would be less usual. For example, let's go ahead and draw on the same graph 2 bell curves with the same mean, but different standard deviations. In this case, the first graph that I drew has a small standard deviation, and the second one has a large standard deviation. We can see in this instance that both graphs are centered around the same point. But for the taller graph with the smaller standard deviation, much more of the data is very close to the center, and there's not very much that's far away. Whereas with the large standard deviation, the data is much more spaced out. Much of the data is further away. The standard deviations of the first graph would look something like this, very small distance. Whereas for the second graph, it might look something like this, a very big distance for one standard deviation. So the larger the standard deviation, the more spread out the graph is, the more spread out the data is, more variation in all of the pieces of data. We'll sometimes talk about the standard normal distribution, which simply has a mean of 0 and a standard deviation of 1. This can be helpful if we're doing very theoretical math about a standard deviation, but we'll more typically have a mean and a standard deviation that applies from some known data set. In either case, this is the notation that we will use, similar to the notation for a binomial distribution, but we'll use an n instead of a b, and we'll mention the mean and the standard deviation as the pieces that we need. One way that we can help make the standard deviation more accessible is to discuss the empirical rule, which talks about how the data is gathered within a certain number of standard deviations. Within one standard deviation of the mean, you would expect to find 68% of the data. Within two standard deviations of the mean, you would expect to find 95% of the data. And within three standard deviations, you would expect to find 99.7% of the data. This, I would expect you to memorize. It's called the empirical rule, but sometimes also known as the 68, 95, 99, 7 rule for obvious reasons, or sometimes the golden rule in statistics. And it is used for us to have a good approximation for what standard deviation means. You could have a standard deviation. You could say, oh, I'm 3 standard deviations above average. And that will tell you, oh, I know that 99.7% of the data is closer to average than this thing that's 3 standard deviations above. So it gives us a sense of how unusual some certain value is based on how many standard deviations from the middle it is. 1 standard deviation, about 2/3 of the data is closer. So it's an unusual score, but not a very unusual score. 2 standard deviations, 95% of the data is closer. This is starting to become a score that's a little bit exceptional. And 3 standard deviations, this score is extraordinarily unusable. Extraordinarily unusual, because only about 1 in 1,000 scores would be as far from the center as something 3 standard deviations away. We can find the percentages for any standard deviation by using a calculator. And we'll take a look at how that works using Google Sheets at the end of this video. For these 3 things, we would like you to have this memorized so we can do quick estimates by hand and have a general sense for how unusual something is. Once again, 1 standard deviation, not particularly unusual, but a little bit. 2 standard deviations, starting to be a little unusual. 3, it's very, and then anything beyond that becomes extremely unusual to the point of where you would be very shocked to see it. Let's take a look at an example here. The mean height of 15 to 18-year-old males from Chile in the years 2009 to 2010 was about 170 centimeters and had a standard deviation of 6 centimeters. Now, height is one very common thing that follows a normal distribution. So let's suppose we let X represent the heights of the 15 to 18-year-old males from Chile in this current time period. Then we would use this notation to indicate that X is normally distributed with a mean of 170 and a standard deviation of 6. By using the empirical rule, we can make statements about certain proportions of the population. 68% would be within 1 standard deviation, which is 6 centimeters. So plus or minus 1 standard deviation here. 95% will be plus or minus 2 standard deviations, so 12 centimeters. And 99.7% is plus or minus 3 standard deviations. If you saw someone that was more than 18 centimeters above the mean, 170 in this case, then you would know that that individual was very, very tall, taller than 99.7% of people. Now, one thing that we can use in order to discuss how many standard deviations away from the mean you are is the idea of a z-score. We've got this fancy formula for the z-score. This is just a way of calculating how many standard deviations away from the mean are you? Are you one standard deviation above, two standard deviations below? Are you right on the mean, or something else? You'll sometimes want to have x isolated in this equation because you'll want to begin with a z-score and move to an x value rather than the opposite. In this case, just quickly solving for x, we would see that x is equal to z times the standard deviation plus the mean. Which makes sense. The whole point is that if I start at the mean and move the z-score, number of standard deviations, we get right back to the data value. A positive z-score would indicate that x is above the mean, whereas a negative z-score would indicate that x is below the mean. Moving back to this same bell curve graph, we can label the different z-scores. This would be a z-score of 0. At one standard deviation away, that would be -1 and 1 on either side for one standard deviation away. Similarly, -2 and 2, and -3 and 3. We can extend the bell curve out, whoops, in order to match all the way. And this bell curve extends indefinitely, but it gets lower and lower and lower the further you go away, because it's much less likely that someone would fall in that range. Let's do some examples using z-scores. The SAT and the ACT, two common college entry exams, are normally distributed. Let's say the SAT has a mean of 500 and standard deviation of 110, whereas the ACT has a mean of 21 and a standard deviation of 6. It's very difficult without using statistics to compare the SATs and the ACTs, not only, of course, because the exams wildly vary in the types of questions that they might have, but also because the range is so different. SAT has a maximum of 800, whereas ACT a maximum of 36. So comparing these scores is challenging, but statistics lets us do it more easily. We're looking to see how many standard deviations away from the mean we are. So let's draw these two graphs, one above the other, scaled so that the standard deviations are the same size. On the top, let's put the SATs. It says the mean here is 500. We'll want to label 3 standard deviations on each side. And it says that the standard deviation is 110. So this would be 610, 720, 830, and then on the other side, we would have 390, 280, and 170. Now, in this case, remember I said SAT has a maximum score of 800, yet I've got 830 on my graph. The SATs are not actually perfectly normal distributed because there is a hard maximum that you could possibly hit. That being said, the normal distribution is still a pretty good number until we start getting very close to the extremes. Similarly, let's sketch the ACTs. Let's make this a little bit closer to scale. That looks pretty good. This one has a mean of 21. We'll sketch in 3 standard deviations on either side. Says the standard deviation is 6. That would be 27, 33, and then 39. Then on the left-hand side, 15, 9, and 3. Notice in both cases, remember I said the maximum ACT score is 36. The highest level of 3 standard deviations above is a little above the maximum. So in this case, both of these suffer the same problem, which actually makes it easier to compare among the two. Now we can say things like, oh, a 33 on the ACTs is kind of like a 720 on the SATs, because those are both 2 standard deviations above average. So we now have a way to compare the two. For example, let's take a look at Maggie's scores. It says Maggie scored a 555 on her SATs. That would be a z-score of 1/2. We can calculate that by using the formula if we would like. So in this case, x is 555, which means z would be 555 minus 500 divided by 110. That is, recall the formula, x minus the mean divided by the standard deviation. So that is 55 over 110, which is 0.5. For the ACTs, x is 19, which makes z equal to 19 minus 21 over 6, negative 26, or negative 1/3, about negative 0.333. Okay, Maggie's SAT score was a little bit above average, and her ACT score was a little bit below average. Neither score was particularly high or particularly low, but her SAT score was above average, whereas her ACT score was below average. This is good information. Let's take a look at Meredith and Derek's scores here. In this case, it says Meredith scored a 700 on her SATs. X is 700, which means that the z-score will be 700 minus 500 divided by 110. 200 divided by 110. We'll shove that into our calculator real fast. Gives us 1.82, give or take. Whereas Derek scored a 34 on his ACTs, z would end up being 34 minus 21 over 6. So that is 13 over 6. Comes out to about 2.17. Derek's score is more above average on the ACTs than Meredith's score was on the ACTs, because he had a larger z-score than she did, which meant that his exam fell around here on this graph, whereas her exam fell around here on this graph. Again, we're comparing different exams, so it's hard to make a direct comparison, but his score was more above average for that exam than her score was for her exam. Finally, this one asks kind of the opposite question. April, in this case, scored in the 97.5th percentile. What score did April get? Now, recall the empirical rule. 68, 95, 99.7% of the data is within 1, 2, or 3 standard deviations. So that means that, for example, right here we have 64% of the data, 68%, excuse me. But that's split on 2 halves. Let's go ahead and match up this like so. If 68% is in here, then that's 34% here and 34% here. Kind of like how you have to divide in the Venn diagrams. Similarly, if we go out additional standard deviations, let's go ahead and erase this green so that we can get a clearer picture. Whoops. Then in this next chunk, it should be 95% for the whole thing. Let's give ourselves a little bit more space. 95% for the empirical rule should be in here. We've already used 68% of it in the centerpieces. So that leaves us with 27% to go in this chunk here on both sides. Half of it on each side would be 13.5% here and here. Similarly, since we need to get 99.7% in the next chunk, we've already used 95, leaves us with 4.7%. So that's 2.35% on either end. In the very extremes, everything beyond that would be 0.15% on either side, to add up to the total of 100%. Notably, these 2 parts right here represent 2.5%. So if April scored 97.5%, that would be everything up to and before this point, 97.5%. So what this is really saying is April scored 2 standard deviations above average. That's 720 for the SATs, and same rule applies for the ACTs, 33. Let's do another example dealing with standard deviations. Let's look this time perhaps at the score of a final exam for a regular class, graded on a standard scale from 0 to 100. So in this case, the mean is 70. That's usually what we expect for an exam of this type. Standard deviation is 5. Supposing that we choose a random score, we want to find the odds that the score is within certain possible ranges. We can use that specific graph to come up with probabilities. Let's create the graph for our exam. So the mean here is at 70. Then we'll sketch 3 standard deviations on either side. So that would be 65, 60, 55, and then 75, 80, 85. We need to find the odds of the scores in certain ranges. First, we want greater than 75. Okay. So we're looking for this piece here. I would always draw and shade this graph in. We know that 68% is in this range. That leaves us with 32% left. 16% here and 16% here, because it's a perfectly symmetric graph, perfectly balanced, as all things should be. So that means that there's a 16% chance that the score is greater than 75. Let's do the same thing for the next part, wanting us to talk about the odds that the score is less than 60. Well, we know that 95% are between 60 and 80, which leaves 5%, 2.5% here, and 2.5% here. So 2.5%. Now for the next one, we're going to have to do a little bit more of the graph out, because it wants the odds now that we're between 65 and 80. Well, we know some of these percentages. 68% that we're in this range, and 95% that we're in this range. Let's fill in individual pieces just like the Venn diagram. So we'll go ahead and mark this, 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 and this as barriers. And we just need to add in the 3 purple shaded regions. These 2 we know for sure are 34%, because that's 68 divided by 2. Of the 95% that's left, taking away the 68, that gives us 27% left to go. So this part and this part add up to 27%. Dividing that by 2 gives us 13.5% on either side. Therefore, to add up, all we need to do is take both of those 34s and the one 13.5, which gives us 81.5%. Now, all of these last ones ended up being things that lined up nicely with the standard deviation, but this one says less than 63. We won't be able to solve this using the empirical rule. What we'll have to do instead is use our calculator. Let me go ahead and show you how we would approach this in Google Sheets. The first thing I would do is I would write into Google Sheets the mean and standard deviation for my problem. I would then put in the specific x value that we're looking for. In this case, 63. Then we will use the function norm dist. Doesn't matter whether or not you choose the one with the dot. You don't want the one with the S. The S is for a standard normal distribution. Remember, that means we have a mean of 0 and a standard deviation of 1. We don't want that here. We want a mean of 70, a standard deviation of 5. So we'll use norm dist. It tells us we need an X, a mean, a standard deviation, and then a cumulative. We will always choose cumulative to be true, because what this will tell us is what is the shading, what is the percentage chance that you are less than or equal to this value. So in other words, let's go ahead and write that all out here. Norm dist, with or without the dot, of X, the mean, the standard deviation, and then you'll always type true, is equal to the probability that our X value is less than, let's actually change this here. Instead of calling this X in the function, let's call this P. It's the probability that X is less than P. So you're choosing a specific number to check what our equation is less than. The probability in this case that our score is less than 63. So we'll type in all the pieces. The 63, we need the mean, the standard deviation, and you'll always type true as your final option. We're never going to use false in this class. It gives us 0.0807, which we know is 8%. There is about an 8% chance that the score will be less than 63. Let's go ahead and write that down, and then we'll look at the next one. Greater than 71. Now this function always does less than. So let's sketch what it's looking for. For this first one, we knew the mean was 70, so that means 63 is here. We were looking for this part. For the second one, the mean is here. We're looking at 71. We're looking for this part. Now, this function can only find the area to the left, area less than a certain number. So if we want the area to the right, we'll just simply need to take the area from the left and then do 1 minus it. So in this case, let's change our X to be 71. And we see that that changes our percentile now to be about 58%. So we will need, I might call this one greater, 1 minus the percentile, which gives us about 42.1%. This next one wants between two numbers. So let's go ahead and sketch what that looks like. We've got still the mean at 70, 62 over here, 77 over here, and we're looking for this here area. The easiest way to do this is to first find this part using a normal distribution, and then to find this part, and then to subtract them. So we'll need two parts here. Let's make a second row. So we'll call this percentile 62, and let's call this one percentile 77. I'm just going to go ahead and instead of including this row at all, let's just type it in. 62. And for this one, same formula, but I want 77. And I want it to have the same mean and standard deviation. So here and here. It gives us two percentages. Therefore, the answer will be equal to the difference of the two. In this case, 86.4%, give or take. It's worth noting here that before calculators were readily available, the best way to calculate this kind of thing was by using a z-table. A z-table is a big list of possible z-scores and their corresponding probabilities. You would just have to have one of these with you if you needed to find a probability at any given moment. We're not going to be looking at z-tables in this class. You're always welcome to use Google Sheets or Excel or another calculator when calculating z-scores, because no one really does this by hand anymore. We can similarly use inverse norm to do the opposite. Given a percentage, find a z-score or find a value. So in this case, let's go to a new sheet here. We want to start with the percentile, given also the mean and the standard deviation. It gives us 0.84, we'll put it in as a decimal, and the same mean as before and the same standard deviation as before. Let's put this for score. That would tell us the score that we would obtain. The function we're looking for is norm_inf. And again, I don't care whether or not you use the dot. It's an identical function. But you don't want the one with the s, because that would be for a standard. If you use this one, it would give you out a z-score. If you use this one, it will give you out an x value. Let's use this one here. So we would put in this percentage, this score, this standard deviation. And it tells us that a score of about 75 would end up being greater than 84% of all other scores. This makes sense because we looked at 84% earlier and saw that that was one standard deviation away. So we got about 75. That was what we expected. For the next part, it asks us about 95%, but notice it says less than here. In this scenario, because it wants less than 95%, we're actually looking for 5% from the bottom. So we should use a percentile of 0.05 or 5%, and it gives us a score of about 61.8. By using z-scores and standard deviations, we can talk about things with a normal distribution, talk about how spread out the data is, and compare it. We'll be able to use this in the next chapter to determine how unusual a piece of data is and to determine whether or not a specific sample is particularly unusual. That's all we've got for today. We'll see you next time.